Okay, so I guess today we'll have to do it without the screen, unless somebody has a VGA to HDMI adapter, because I forgot mine. Anyway, it's good. At least we'll have something on the board. And I'll upload the lecture notes written nicely for those people who are hoping for a webcast, so they'll hear my voice and then hopefully be able to follow in the uploaded lecture notes. So what we're going to do today is go through the frequency analysis for both a transistor and kind of like a single stage amplifier, as well as I'll give you some tools with which you'll be able to go and do frequency analysis of multi-stage amplifiers or whichever systems have sort of a dominant pole in there. And that's kind of what the homework will be about this week. We will also start the lab this week. So that's kind of the big event. And so we have Tuesday and Wednesday slots, as we talked about, with Wednesday being kind of the focus lab slot and Tuesday being more office hours with some kind of time for people to do the lab if they can't do on Wednesday. Okay, so we're going to start by looking at the frequency analysis of BJT and MOSFET. And given that both of these devices are essentially current amplifiers, in a sense, the first thing we're interested in when we look at them is what is the current gain, or at least at what frequency does the gain cease to exist, right? So what we're going to have is we're going to label FT as this frequency of unit gain. Where so we'll call it short circuit output current equals input current. So if you go and draw a transistor, so I in that goes into the gate will essentially be equal to the I out that's grounded in the case where we're looking for this short circuit unity gain frequency. So if we go and write out the small signal model for the transistor, including kind of all the parasitic capacitances that we talked about. So we have CGS plus CGB. Then we have CGD. And then we're actually grounding the output, right, and looking at the output current. Now, I'm really looking at this output current, but because the R naught is grounded, it's the same. There's no current flowing through it because the voltage is 0. So I can say that output current is really just GM VGS. Okay. Now we can go in and write out sort of the phasor KVL, KCL for this case, assuming that now these are some impedances, omega or transmittances, omega, CGS, CGD, etc. So just for ease of it, we're going to label this current through CGD as IX, just as sort of intermediate variable. So what we can write is that I in is VGS, so VGS will be here, times j omega, and then, so the I in will be here. Whatever the total impedance here is. Now, given that the output is grounded, the other side of CGD is grounded, so I really have just these capacitances in parallel. So that will be j omega C total, and I'm going to say C total is CGS plus CGB plus CGD. Okay, it's kind of an important parameter. And then we have, for I out, that will be this GMVGS minus IX. And then I can say that IX is, this is really current flowing from VGS to ground through CGD. So it's VGS times j omega CGD. Okay. From these, we can write out I out as GM minus j omega CGD times I in over j omega CT. And I can then write out the I out over I in. The magnitude would be the magnitude of GM minus j omega CGD over magnitude of j omega CT. Now, if I assume that CT is a lot bigger than CGD, or I'm assuming that omega t is much, CGD is kind of much smaller than 1, than GM. Then we can approximate this as just GM over j omega CT. Or better said, I'll just do this at this FT frequency, so that we're going to say that I out over I in at omega t is GM over omega t CT. And then we're going to say this is 1 by definition. I'm looking at omega t, which is the frequency at which this ratio is 1. Okay? So then omega t is equal to GM over CT, or and now you see from here that since omega t CT is GM, then my assumption here, this was omega t CT, is really that CGD is much smaller than the total sum of capacitances, which is CGS primarily. Right, so I'm assuming that the overlap cap is much smaller than the real main gate source cap, which in most cases is the case, but in modern technologies, CGD extrinsic is actually increasing quite a bit. So, great. This FT is somewhere between 10 gigahertz and 300 gigahertz. Actually, in modern technologies, like 30 to 45 nanometer, even lower, you're getting somewhere into 200 to 300 gigahertz range. It's mostly actually limited by the extrinsic capacitances right now. but this is kind of the limit. Okay, so if we go one step further just from here, we can kind of see an interesting development. So our ft will be equal to gm over 2 pi cgs. I'm approximating here ct with cgs, because I'm assuming that cgs is the most dominant term. And that allows me to kind of develop gm further. So I'll say this is mu n cox prime w over L times vgs minus vt over 2 pi times 2/3 and a cgl cox prime times w times L. So when we cancel a bunch of stuff here, we're getting something that's like 3/2 mu n, and then I have VGS minus VTH over 2 pi times L square. This is kind of an insightful equation, because it tells you that there's two knobs to tweak FT in the MOSFET. So one is L. So the smaller channel length I have, the bigger actually my FT. And granted, L square is for this devices that don't suffer from velocity saturation. In reality, in modern sub-100 nanometer devices, this more depends on like 1 over L than L square. But still, L is a good knob. And then there's another term here, VGS minus VT, means that the more current you pump into this device, or the more VGS you have, actually you can improve the FT as well. So that's kind of an interesting design parameter for a FET. Now, just to contrast that with bipolar, for BJT, what we have is kind of a similar situation. So we're going to have, I'm going to say here I'm driving it with I in. And then I have R pi, C pi, C mu. And then GM VBE, where VB is across here, base emitter. Emitter is grounded. And then again, I have R naught, and R naught is shorted to ground. Okay. And we're looking at I out. So we can write that VB is I in times, and then we have a parallel connection of R pi with C pi plus C mu. Right? So that's 1 over j omega C pi plus C mu. And I can write that out as I in times R pi over 1 plus R pi C pi plus C mu j omega. So I out will be GMVB, which is this current, and then I'll also label this as IX, the current through C mu. Oh, sorry. I guess, OK. So we have GMVBE minus this current IX that flows through. So very similar situation with so now we can, for simplicity, we'll neglect the IX because it's going to end up being the same thing as here for getting this parameter, j omega CGD. It's again relying on the fact that C mu is a lot smaller than C pi, right? So just to get there quicker, I'll say that beta of j omega, which is our current ratio, which is I out over I in. In that case, I just essentially divide these two, right? So I'm getting GM R pi over 1 plus R pi C pi plus C mu J omega. And notice something interesting here. This is now beta 0. And then I can write the denominator as also beta 0 C pi plus C mu over GM J omega. So if I neglect this factor of 1 here, can essentially approximate beta as GM over C pi plus C mu J omega. If we take another look at that, so I'll rewrite it here. So for beta equals 1, we have that omega t is again GM over C pi plus C mu. And this is, again, C pi plus C mu is kind of like our C total for the FET. So it's essentially exactly the same relationship. Right? Now, in this case, FTs are somewhere between 100 gigahertz to 300 plus gigahertz. So it used to be up until like 5 or 6 years ago that you couldn't beat the bipolar FT with a MOSFET. They're way slower. But as we saw, MOSFETs have this nice characteristics that you can kind of drive them more to get better FT. And with very, very small technology, you can kind of start getting into the range of the bipolar FTs. Now, let's take a look a little bit through this expression. Where does this capability come from? Like GM, okay, we know, but like what physical parameters? If we say that the time constant, which is the inversely proportional to this omega t, or the unit frequency, is C pi over GM plus C mu over GM. We can then further develop this GM and C pi. And if you remember what C pi is composed of, it's CB plus CJE over GM. Now, when we did the derivation for CB, we related that to tau f, which was the time of flight across the base, right? So this factor CB over GM was actually tau f. And then we actually derived how tau f depends on the geometry of the base. So if I assume that this is really, I'm kind of giving it a discount here, assuming that this is much more dominant than the rest. So then my ft is 2 pi tau f. And that's indeed true when we have large currents and large GM. Then mostly the transport time will be dominated by tau f. So this will be equal to 2dn over 2 pi times wb squared. And now I'll use the Einstein relationship for dn. So dn over mu n was kt over q, and that was our vt. And this is just to try to better relate a little bit to the MOSFET expression. So we have from here that 2 mu n Vt over 2 pi Wb squared equals Ft. So compare this to the MOSFET expression that we had here, right? You see that both depend quadratically, inverse quadratically on the smallest dimension that you have through which electrons are flying through, right? So here it's channel length squared. Over there it's base squared, base length squared, Wb. But the important difference is that while in the MOS you can actually crank up VGS to improve the Ft, in bipolars you can't. You're kind of pinned to this Vt. And so this is another, even though MOS is kind of inferior, it has this extra knob that allows you to trade power for speed, essentially. OK, so this is kind of a rundown through the bipolar, just like what limits the, and MOSFET, what limits the current. But I want to jump in right now into kind of what are the properties of the amplifiers that we create with these frequency-dependent components. Just so I can give you the basic tools. Okay. So when we look at the amplifier, this is amplifier frequency response. What we're going to see is something that looks like this. There will be a certain frequency, omega L, below which we're not going to get any signal through the amplifier. And this is mostly because we're putting these blocking biasing capacitors. So we're going to say these are from bias Cs. And normally, we assumed in our analysis so far that these are so big that very quickly after DC, you essentially these become short, right? So 1 over omega C bias. If that C bias is going to infinity, then this omega L is like really, really close to DC, right? But in reality, it will be a few tens of kilohertz or something like that, depending on what size CL. If you're using CLs in microfarads, this omega L will be kind of in the range of tens of kilohertz, right? And then we have this other. So this is intentional. Omega L is what we add to the circuit, right? Now, unfortunately, what you're going to have also is what Mother Nature added to the circuitry. And that's this omega H, which is the cutoff. So this is the high cutoff frequency. And this one will be because of the C's internal to transistor. Right. Those are our CGS, CGD, CMU, CPIs, etc. Whatever technology we have, this is going to be due to the transistor. And this band, or this flat curve in terms of amplification, we're going to call midband. This is where our amplifier achieves the behavior we want. Now, if the amplifier is DC coupled, meaning there's no bias transistors that prevent the signal from propagating, DC signal from propagating to the amplifier, then we simply are going to have a situation like this, where this midband gain extends all the way to DC. Right? So sometimes you're going to have omega L if the system is AC coupled. And then you're also sometimes, if it's DC coupled, you're not going to have that. You're just going to have the cutoff, the high frequency cutoff. Right? So there will be different problems that you'll see that will have different formulations in this sense. And we'll be using different approximations to solve for these frequencies to understand roughly where things are. So in general, when I see a curve like this, you can really describe it as A of S is A0 times, and then like polynomials in S, right? Plus so the first polynomial goes to the degree number of zeros in the system, and then the second polynomial in the denominator goes to B number of poles to S number of poles, where number of poles is greater or equal than number of zeros. And we can rewrite that, obviously, as something that looks like a ratio of the two products of S over Zi, or I equals 1 through NZ, and 1 minus S over Pi, where J, let's call it J, where J equals 1 through NP. Obviously, this is very cumbersome to keep track of all these poles. So when we do the analysis by hand, we're mostly going to take a look at the dominant pole, meaning 1 minus S over P1. Right? And we're going to be assuming maybe we find the second pole, non-dominant pole if the system is two-pole. That's as far as we're going to go. And we'll see that some approximation methods ignore zeros. Usually, unless zero is intentional in the circuit, it's kind of like higher frequency. So we're mostly going to be focused on the poles. And then this A0 is our DC gain. Because when all S's are 0, then you just get A0. Right. So I'm going to show you a few tricks that we're going to use in our analysis toolbox. Because if you try even on a single common source kind of single transistor stage, try writing everything by hand and solving KVL, KCL. It's going to take a while. In chapter 7 in the book, you can take a look at this. I'm not going to do it just because it will be a 2-hour lecture. But even that is kind of a little bit involved. So we're going to do a few tricks. So one is that we're going to use is Miller theorem, or approximation. And what this says in general is that if I have an LTI system which has an impedance that sticks out, let's say it's called ZX, and then I have input current IX and voltage VX on one side, and I know that the voltage on the other side is AVX. Okay? Then I'm looking at how to take this bridge impedance and terminate it to ground on both sides so that I still get the same currents flowing. So that this LTI system doesn't really know that I've cut the impedance in half. Okay? So what I'm looking for is this, where on the left I have some ZY, but same current IX flows and VX is the voltage. And then here I have some ZZ, where, again, I have voltage AVX. And the current is in the opposite direction, so this is minus IX. Right? So if I look at this, the expression for the current, then IX is VX minus AVX over ZX. And it also, from this modified system, is Vx over Zy. So I immediately have expression for Zy. I can take out Vx's, and what I'm left is Zx of 1 minus A. This is kind of the most important part of the Miller approximation. What it says essentially is that I'm dividing the impedance by 1 over 1 minus the gain. Now, this is actually totally exact. But if I have really like capacitance and inductors, then this A is a function of omega. Right? So I would have to know what A of omega or A of S is. And in general, I don't know that because that makes things very complicated. So the approximation is that I'll assume that A is A0. So I'm just assuming that A is basically my DC gain. Or if I'm calculating sort of mid-band gain, then it's my mid-band gain. Okay? So we did that. Then the approximation is Zx is 1 over 1 minus A0. And now for the other ZZ, I have AVX minus VX over ZX. That's this current. And that equals to AVX over ZZ. So that's essentially this current. And when I equate these two, I get that ZZ is minus A over 1 minus A times ZX. Now again, I'll make A equal A0, and that will be my expression for the approximate impedance. Now, what that means is that if my amplifier characteristic is something like this, where I have my A0, and then I have pole 1 and pole 2, and here I have minus 20 dB per decade, and here I have minus 40, because I'm after 2 poles. Okay, then my Miller approximation is going to be valid where? Where? Yeah, it's going to be valid around here, right? So if I'm trying to determine my first pole, it will still be OK. Right? But if I'm trying to determine my second pole, then it's not going to be OK, because my A of S is already, who knows, maybe 10 dB down, right? So then my impedances are maybe off by 10x. Okay? So Miller is good for dominant pole. But after that, it really breaks apart. Okay? And as we're going to see right now on a common source example, ZY and ZZ will give you 2 poles. Okay? But you'll have to choose, depending on circuit parameters, which one of these 2 is more dominant. And then just use that one. Then the expression for the other one is not going to be valid anymore. Right? OK. So we're going to do that over here. So actually, before I jump to that example, let me just give you Let me just give you a little spiel about the second tool, because we may actually run a little bit out of time, and I want you to know that tool so you can start doing the homework. Okay? And then I'll prove you that sort of Miller and this tool are roughly equivalent. So in addition to Miller, we're going to use another tool which is called zero circuit time constant or open circuit time constant. And what this basically says is that if I look at the coefficient B1 that I had in my polynomial in my transfer function, then you can sort of prove that this B1 is equal to the sum of the reciprocals of the poles. Okay, just the way you multiply out the equation, the polynomial, or the expressions for poles. And 1 over pole, we're going to call this a time constant, right? So we're going to say that this is the sum of I of Ti of the pole. Okay. And each one of these pole time constants we can examine by taking a look at the with this ZCTC method. So we're going to say we pick CI, and then keep all other, or let's say pick CK. Pick all other CI different than K open. And then calculate R seen by CK. When we say seen, hopefully by now, when we say what resistance you're seeing, you know how to do it, right? So you short all the independent sources, you apply VT, you test for IT, or you apply IT, test for VT, right? So that's it. The only caveat here is that when I do this stuff, I want to keep all my bypass caps shorted, right? So we have to separately consider bypass caps. So why is it? Because we said that bypass caps have a certain behavior, like way at low frequencies, right? And when we're analyzing the pole, the dominant poles from parasitics, we don't want them to play a role, okay? So because they're going to be so far down, by the time we're analyzing what's happening around the pole, all the capacitors of the nature 1 omega C bias should be like 0 resistance, right? So I can assume that they're shorted because they're so big. So this is kind of one important thing to keep in mind. And so now that we have the tool, we're going to go first do the Miller, and then we're going to come back and do the common source with this approximation as well. Oh, actually, let me give you a third one as well. Just to confuse you a little bit even more. So what we have with zero circuit time constant is that I can take B1 and accurately represent it through a sum of these pole time constants. But now, if one pole is much smaller than the rest, then I can say that this 1 over that pole really dominates this sum. So what I'm really going to have for dominant pole, let's say P1, that P1 will be equal to 1 over sum of TIs, TPI. So by calculating what is the sum of these individual pole time open circuit time constants, I'll get a really good approximation for the dominant pole. And furthermore, if you take a look at these individual time constants, you'll know also where it comes from. Because usually in circuits, it's going to happen that only one of these open circuit time constants is like really big, and the rest are like really small. And that means that that part that's causing that large time constant is actually the culprit. That is the piece that limits the bandwidth in your circuit. And you can go and fix it if you can resize the transistors or change the resistors a little bit to make that happen, okay? So it's not only an approximate tool for doing stuff, but it also kind of nicely gives you intuition about what to fix in the circuit. Now, we're going to use another method to determine sometimes what's the highest pole that we can get in the circuit. Okay, and for that, we're going to use the method that's called short circuit time constant. What this really means is that I'm going to have that the sum of the poles is the sum of 1 over, let's call this I as well. So now the sum of poles is equal to the sum of the inverse short circuit time constants. So notice here, largest pole let's call it, let's say that's PNP, if I've ordered my poles nicely. PNP will now be approximately equal to the sum of 1 over tau SIs. Okay? So in this case, my largest pole is equal to 1 over sum of the time constants, open circuit time constants. In the other case, my largest pole, my most non-critical pole, so to speak, right, is sum of the inverse short circuit time constants. How do I find short circuit time constants? Same way as I'm finding the open circuit, just whenever I look from capacitor C, I short all the other capacitors. Why am I shorting? Intuitively, I'm assuming that this pole is so much better, further out than anybody else, that all 1 over omega C's are actually 0, right? That's why I'm shorting all those guys. So this kind of thinking really is going to give you intuition to solve these problems. For example, what we can use this SCTC, we're going to use it in 2-pole systems. So with ZCTC, we're going to calculate P1, which is the dominant pole. And then with this one, we're going to calculate P2, which is the non-dominant pole. That's exact for 2 poles. Okay? We can also use SCTC if we're looking at calculating omega L, which is the cutoff frequency for this guy. But why is it? So I know that this omega L is composed only of the capacitors that I add. They're so much bigger than all the other capacitors in the circuitry, right, from transistors. So what I assume here is that when I'm calculating omega L, all transistor parasitics are open. All C's are gone, okay? Because the frequency is so low that 1 over omega C parasitic is really a really high impedance. And then I'm looking, just zooming in here, where are the poles that these individual capacitors, bias capacitors, are introducing, right? And I'm looking for the furthest one, because the largest of those is flattening this curve. Does that make sense? So if I have 3 bias capacitors, one pole would be here, maybe one here, and one here. Well, this one is going to completely dominate, because that's the one that's going to flatten the whole thing. Okay? So by using short circuit time constant, then I'm looking at that largest pole. Right? But for the omega H, I'm always applying open circuit time constant, because I'm looking for a first pole that shows up, okay, from parasitics. At that point, my biases are already shorted. Okay, so these algorithms are important to keep in mind when you start doing the circuit analysis. Okay, now we can go and take a look at the Miller example. So we're going to do a VI, RS. We have a CGS, CGD, and then GM-VGS, and then RD. I'm assuming that RD is much smaller than R naught, so just so it'll be easier. Now, CGD is our bridge, okay? So we're going to use, and I know that I have VGS here, and at DC, what is my output as a function of VGS? At DC. If I'm applying a voltage here at VGS, what is my output? Yeah, minus GMRD, right? Because I'm pulling, yeah. Okay, so what is my A? Yep. So A, or I can say A0, is minus GMRD. So then I can apply that to this guy and break it. So I'll have VI here, RS, and I have CGS, and then here I have CGD times 1 plus GMRD. Right. I'm dividing the impedance. I'm multiplying the transmittance. Right. And then on this side, I have RD, but I also have in parallel CGD. I'll just keep it as A minus 1 over A. Okay. So now I can now start writing some stuff. So VGS over VI is 1 over 1 plus SRS CGS plus CGD 1 plus GMRD. Hopefully, this is understood because this is just RS into a total capacitor, right? So that's 1 over 1 plus SRS. And then this is the total capacitance, CGS plus CGD. Okay? And then we have V out over VGS. And that is, again, minus GM times the total impedance here. So RD in parallel with, well, let's say, parallel with 1 over J omega CGD A minus 1 over A. Okay, and that equals minus GM RD over 1 plus J omega. Did I use S? Yes, S. Okay, fine. What's S? RD CGD A minus 1 over A. Okay, this is actually interesting because when I multiply, so here I have a single pole, right? And that pole comes from this capacitor, CGS plus CGD. Okay. On the other hand, if I look at this, I also have a pole. So we said Miller is only good for one of the two, right? The one that hits first. So I need to be able to plug in kind of the values and see which one is most dominant. Okay. So this one over here, we're going to call it pole 2, and it's approximately dominant. It's approximately 1 over RD CGD, and then 1 plus GM RD over GM RD, and that's approximately 1 over RD CGD. Okay, because this is approximately 1. Now P1 will be 1 over RS times CGS plus CGD 1 plus GMRD. Okay. And when you plug in the numbers, sometimes one, sometimes the other will be more dominant, and that will be the one that actually is valid. Okay, so let's keep this expression just for a moment, and let's do quickly a ZTC. I'm not going to redraw it, but I'm just going to say that the first time constant will depend on CGS. And so we're looking at RGS open. That is when we open this capacitor, and then we're looking from this side. So I'm going to draw it just once so you have it. So we have RS with input shorted. We're applying V test and I test. My CGD is open. And then I have whatever's on the other side that doesn't matter. So really, RGS is RS. And then I have, for CGD, I have RGD open. And that is a little bit more complicated, because now we have RS. And then we have, instead of CGD, we can apply I-test and measure V-test. And then over here, we have GM VGS. And then we also have RD. So if I go and write this out, my VGS will be RS times I-test. And then my I-test will be minus GM VGS, and that's RS I-test. And then will be minus RS I-test, which is VGS, minus VGS, V-test, over RD. From this, if we sort it out by VT and IT, we get RD, which multiplies 1 plus GM RS plus RS over RD. So my RGD is essentially RD plus RS plus GM RS RD. And then my dominant pole is going to be 1 over CGS times RS, which is our first constant, plus CGD times RS plus RD plus GM RS RD. Notice the similarity of this and that piece. We have CGS times RS. We have CGD times RS. And we have CGD times GM RD RS. The only thing that's missing was this CGD RD. Okay. If you go look at chapter 7, for this example, the exact expression is essentially this one. Okay. So Miller does screw up a little bit. Okay. But assuming that GM RS RD is really the most dominant factor of these three, it's kind of OK. Right? Now, if we quickly apply the short circuit time constant, for which I'll just do it for a minute, and we may get cut off for the broadcast, but just for your sake. For pole 2, we're going to have 1 over 2 short circuit time constants. And then the first one will be from CGS. So RGS short will be and then I just short CGD. And then here, because I'm applying the same test, so this is GMV test, so then my RGS is really RS in parallel with RD in parallel with 1 over GM. And then for